My name is Holger Großhans and I come from Physikalisch-Technische Bundesanstalt, the German National Meteorology Institute. I present today a new measurement system that can resolve in space the electrostatic charge of powder flows. My co-workers on this task were Dr. Wenchao Xu. He made all the experiments and he developed the actual measurement system. Dr. Simon Jantac, he contributed to developing the measurement system. And Professor Tatsushi Matsuyama, he helped us designing the test rig. And now, let's jump straight to the key result of our work.
This is the charge of particles resolved over the width of a conveying duct. So here we have the left wall of the duct and here we have the right wall of the duct. And we see that we have large charge peaks close to the walls, a positive one to the left and a positive one and a negative one to the right. And the dashed line shows the average charge as it would have been measured by a Faraday pail. So you see that the charge peaks that we can resolve are much higher than the close to zero charge that is measured by the Faraday pail.
Faraday pails have massively improved our understanding of the charging of powder flows. But as you know, a Faraday detects only the sum of all particle charges. Or if you know the number of particles, then the average charge per particle. Which means, if, let's say, half of my particles carry a high positive charge, and the other half a high negative, the Faraday maybe detects a total charge of 0. This is of course a huge problem for process safety. And also, when you think of all the simulation groups which try to simulate powder charging, we currently have no reliable validation data. Also, there have been some great approaches to determine the charge of individual particles by putting them into an electric field and measuring the response of the particle to the electric field. This works great if the particle is in a vacuum or in a laminar flow, because then you know the fluid forces attacking on the particle. But in general case of a particle in a turbulent flow, we don't know the fluid forces. And what we present today is a measurement system that can resolve the particle charge in a turbulent flow. So now let's go to our lab and have a look at the measurement system.
Hello everyone, welcome to our lab. I'm Wenchao and I'm postdoc in Holger's group. I'm very happy to introduce the electrostatic charge of particles in turbulent flows. The whole test rig consists of a feeder, a vertical duct, a cyclone, a filter, and an air blower. The air, together with particles, enters the test rig from top end of duct. After traveling through the duct, the airflow passes by the cyclone and filter so that the particles are fully separated from the airflow. Finally, the air will be sucked out by the air blower at the end of the test rig. For the charge measurement, we use 2 pieces of ITO-coated PET films and connect them to a high-voltage power supply to produce a homogeneous electric field. We use a pulse laser to illuminate the particles in the electric field and a high-speed camera to track the motion of particles. This is the basic setup of our experiment. Thank you.
And next I will show how from the results of this experiment we can calculate the particle charge.
And now I show how we calculate the particle charge based on its response to the electrostatic field. The first equation here is the momentum balance of a particle in y direction. So this is the direction of the electrostatic field and the direction of the axis of the laser beam. The momentum balance I divide by the mass of the particle, and then we receive on the right hand side of the equation the acceleration of the particle in y direction. And on the right hand side of the equation, specific forces all in y direction. Drag, collisional, electrostatic and gravitational forces. We approximate these terms. This here are the drag forces, where we assume a Stokes flow, so the particle response time is a constant. Electrostatic forces. Here we assume that the electric field strength consists only of the external electric field which we apply to the flow through our electrodes. So we neglect the electric field by the surrounding charged particles or generated by charged spots which are located on the conveying duct. And finally, gravitational forces become zero because our conveying direction is downward and our laser beam is horizontal. We plug in these expressions into the above equation and solve it for the particle charge Q. Now, to look at the terms on the right hand side of this equation. The acceleration of the particle in y direction and its velocity we can measure using our PTV system. The particle response time we know, the particle mass we know because we have monodispersed particles, and we know the strength of the electric field that we apply. But the problem of this equation lies in these two terms. We don't know the gas velocity in y direction, and we need it instantaneously and simultaneously, so at the same time as the particle velocity, to compute the drag forces. Earlier in this talk I said there are excellent works which calculate the electrostatic charge of particles in a vacuum or in a laminar flow. In vacuum this term vanishes completely. In a laminar flow the gas velocity is zero, so we can compute it. But the general case of a particle in a turbulent flow, we don't know the gas velocity. Similarly, collisional acceleration. One could say in a dilute flow particle collisions happen very seldom, but we also know that even in a dilute flow the particle concentration locally can become very high. Locally it can become 100 times higher than the bulk of the flow. And then we can also not neglect the collisional acceleration. So now we want to propose a new procedure to solve this equation based on averaging. We average this equation in time. This bar denotes the time average of a quantity. And what is important, while the previous equations were Lagrangian equations. So this equation here, for example, is for a single particle that we drag in time and in space. This average is for a fixed point in space. So that means, for example, the acceleration, we average the acceleration of many particles passing one point in space. And now we do the same average, but this time for the electrostatic field switched off. And we can assume that no matter if the field is switched on or off, the velocity of the gas phase will not change. And also the collisional acceleration of the particles will not change. At least as long as we measure the equation where the electrostatic field is switched on quite short after switching on the electrostatic field. So we have now two average equations and we subtract them from each other. And the spectacular thing of this new equation that we obtain is it includes the effect of the gas phase and of collisional accelerations, but the terms vanish explicitly from this equation. So that means now we have an expression for the average charge of a particle at a certain point in space, and all terms on the right hand side of this equation we either know or we can measure.
To the left you see the particle flow when the electric field is switched off, and to the right when the electric field is switched on. Both videos are slowed down by a factor of 150. On first view, both flows look very similar. But when you look careful to the video on the right, you see that there are many particles which move with a high velocity towards the left or the right wall. These are the highly positive or negative charged particles which are accelerated towards the electrodes on the left or the right side of the duct.
What you see here are the results of our PTV experiments. To the left, the particle velocity, and to the right, the particle accelerations. Both are resolved over the width of the duct. So here to the left is the left wall of the duct, and to the right wall. These are the velocities and accelerations for the particles when the electric field is switched off. When we switch on the electric field, you can see that the velocities and accelerations clearly respond to the electric field. And this response, the difference between the blue and the orange curves, is what we use to calculate the particle charge. We conducted a second experiment where we pre-charged the particles. So before entering the duct, they received an additional positive charge. And as you can see, this additional positive charge is clearly reflected again by the particle velocities and accelerations, both when the electric field is switched on or off. And this data is what we plug into the equation that we have derived. In blue, you see the curve which I presented already in the very beginning of this presentation. So we see that we can resolve the charge over the duct width, and the flow charged particles have a clear bipolar flow pattern. To the left of the duct we have a positive region, and to the right side of the duct a negative region. The peaks are much larger than the average measured by a Faraday pail. In orange you see the curves where the particles received a positive precharge. Our method resolves this positive precharge because the average particle charge increases compared to the non-precharged particles, as you can see by the Faraday reading comparing the orange and the blue average. To the right side of the duct, nevertheless, the average charge of the precharged particles is lower. This is because the precharging not only just gives the offset to the particle charge, it influences the flow, and the additional charge also influences the flow. So positive charged particles can move from the right side of the duct to the left side, by doing so decreasing the average charge on the right side. But on the left side, the peak of the particle charge increases dramatically. And in this case, for the precharged particle, the maximum charge is 85 times higher than what would be read by a Faraday pail.
We already hold a patent for this technology. We registered the invention in 2020, the patent in 2021, and we got granted a patent for the German market in 2022. This year we applied for a patent for the US and the complete European Union market. Now, at the end of this presentation, I would like to thank the European Research Council for the generous funding of this project and you for your attention.